Welcome. In this session, we'll continue with the discussion on how to use Laplace transform to solve circuit analysis problems. Let's start. Let's solve this problem that is from Alexander Sadiko's book. So let's solve this. So in this problem, our goal is to find the voltage across the capacitor for t greater or equal to 0. So the circuit is as shown. We have a voltage source, independent voltage source, and we have a dependent current source in this. So what we'll do, we'll first convert in order to find V naught of T. What we'll do, we'll draw the equivalent circuit of this. Now this time V naught of 0 means since the initial voltage stored in the capacitor is 0, so we'll replace simply the capacitor will be replaced by simply 1 by CS. Okay, because there is no initial voltage stored. So let's first draw the equivalent circuit of this equivalent Laplace transform model. So we have a resistor. Then we have a dependent current source. Then we have resistor here. Then capacitor will be replaced by an impedance by CS. So have a dependent voltage source here. And let's write the equivalent terms. So the equivalent of 5 delta t is simply 5 because Laplace transform of delta t is 1. Now resistor is replaced by 2. This will be simply replaced by 4 is. Let me write simply I. So where capital I is same as S. Okay, let's use this in order to simplify the notations. So then we have capacitance is 1 farad, so it will be replaced by 1 by CS. C is 1, so it will be replaced by 1 by S. So V naught, it will be V naught of S. So V naught is same as V naught of S. This is the notations. Okay, so we'll drop S in these notations. We know these are functions of now 1 resistor will be replaced by 1. Okay, so this is our circuit, and then we have a current here, I, that is flowing like this. Okay, all right. So our goal is to find V naught of T. So first we'll find V naught of S, or simply V naught here. So as our goal is to find V naught of T, we'll find first V naught of S. So what is the total current flowing here? From this side we have I, from this side we have 4I. So the I plus 4I is 5I. So the total current flowing in this branch will be simply 5I. All right, okay. And let's apply KVL in this loop first. So from KVL, we apply KVL in loop 1. Okay, will give us -5. That's the voltage drop and 5 volt source. Then we have 2 impedance multiplied by current is the voltage drop. We'll write the voltage across this 1 by S impedance as V naught. That's equal to 0. Okay. So we'll simplify this. We'll write V naught is equal to, we'll take these two terms on the right hand side. So V naught is simply 5 minus twice I. This is our first equation. Now, since this is impedance, we can write the Ohm's law for this. What is the total current flowing in this branch? It is 5I. So 5I, that is the current multiplied by impedance. Impedance is 1 by S. That will be the voltage. So V naught. So V naught is simply given by 5I divided by multiplied by S. So 5 divided by S multiplied by I is the voltage across this impedance 1 by S. So if we substitute it here, what we'll get? So let me get I here because we need V naught. So I will be simply equal to S times V naught divided by 5. So substituting this here, what we'll get? So V naught will be simply equal to 5 minus 2s times V naught divided by 5. So if I cross multiply this is 25 minus 2s divided by s. Sorry, let me, because we have a term on this, I have done it wrong. So let me take this V naught term on the left hand side. So we can write it V naught plus 2s divided by 5 multiplied by V naught is equal to 5. Okay, this term I have written on the left hand side. Okay, let's simplify this. Take V naught common. So V naught into 1 plus 2s divided by 5 is equal to 5. So if we simplify this, so it will be V naught into 5 plus 2s divided by 5 is equal to 5. So if we further simplify this, we can write it. V naught will be equal to 25 divided by 5 plus 2s. Okay. Now we'll try to bring it in the form of 1 divided by s plus a. So what we'll do, we'll say V naught is equal to 25. If I take 2 common from this, it will be 2 into s plus 5 by 2. So that will give me V naught is equal to 25 divided by 2 is 12.5 divided by s plus 5 by 2. 5 by 2 is 2.5, or let's keep it like this. Now it's in this form. We know the inverse Laplace transform of this term. So we say V naught of t will be simply equal to 12.5 e to the power of minus 5 by t to 5 by 2 u of t. So this is the voltage across this capacitor if the capacitor was initially uncharged. So this is the voltage across this. Okay. So in other words, once you convert the circuit into the Laplace transform domain, the impedances of the capacitor, inductor, and resistor will behave like resistances. Means in the we can use all the techniques that we have learned for resistor networks. We can apply them to this network. Same thing will be true if you want to use mesh analysis. If you have to solve a network that contains multiple meshes or multiple nodes, you can use the same techniques to solve this that you have learned in this DC analysis for resistive networks. Okay. All right. So let me stop it here.